Hello, everyone. I realize my name is a bit of a mouthful, so you can just call me Leah. That's absolutely fine. My surname isn't very common, even in the country where it comes from. So which is the Philippines. That's where my dad's from. I'm from the School of Metallurgy and Materials at the University of Birmingham, and I want to talk to you today about the QuSIT hub and opportunities that we see going forward as the hub develops to move into space. So in case people didn't know, the Quantum Technologies program has been running for over a decade now. It has just started its third phase as of a few days ago. The kickoff for phase 3 was on the 1st of December. It represents a £100 million investment over the next 5 years by UKRI in 5 hubs, which are scattered around the UK, led by different institutions. Every hub has quite a large number of partners, both academic and industrial, who are meant to help to translate the fundamental research in quantum into end user benefit. So the Quantum Technologies Hub in Sensing, Imaging, and Timing, or QuSIT, this is who we are. There's obviously a large contingent of us from Birmingham, as we are the lead for the hub. And there's a nice picture of us there up at the top. I realize that some people who are in the hub could potentially be in the audience or online. Hello, online people. And I do apologize if I don't recognize you, because of some of them I have only met once. So at our kickoff meeting. So our aim over the 5 years is to try and take the interdisciplinary expertise from researchers across those 11 institutions and work with our industry partners and use our army of PhD students and postdoctoral researchers and move the research that is being done towards commercial exploitation. There's already a number of spin-off companies that have emerged from the QT hub in the previous phases, and there are currently 3 of those spin-out companies actually working directly with the hub now. So there's the logos of a number of partners, not everyone, on the slide, as many as could be fit on there without making just the whole thing logos. So it did just start, but the end goal for QuSIT is to produce these key field trials. So one on exploring underground infrastructure, one on security screening, remote gas imaging, brain health, quantum microscopy, and quantum-enabled radar. And I'm not going to pretend I'm able to speak to all of these. These are not my area of expertise. So I'm going to focus on one of them, which is quantum-enabled radar. So our motivation for trying to use quantum-enabled radar in space is to help to maintain a sustainable environment in Earth orbit. And we want to provide fast and actionable assessment of the in-orbit environment. So the picture over on the left-hand side is just to represent how crowded LEO space is. I think we're all very well aware of that. And the image on the right was created by my postdoc Lily from her lovely Python script, just showing all of the currently active satellites in orbit, as well as in red, debris from the large collision events that have occurred over the last 10 years. So this gives you kind of a sense of just how much there is out there. Oh, it also includes the Intelsat 33E debris that is now populating GEO, and about which we could currently do nothing. So what we want to do about this is to provide a new sensing capability using sub-terahertz inverse synthetic aperture radar. And I've got a number of pictures here demonstrating how the technique works. So on the left-hand side, you can see there's an observed satellite, which is marked OS, and a monitoring satellite, which is marked MS. The MS is where the inverse synthetic aperture radar system lives, and it is in this diagram in a circular orbit just above the OS, about 100 kilometers away. And the technique is different from SAR. I'm sure everybody in the room is familiar with SAR because it's used very commonly in Earth observation, where you have effectively a stationary target, which is the Earth, and the radar is moving. Whereas ISAR relies on the fast relative motion between the monitoring satellite and the observed satellite in order to produce the image. So hence the parameters in the table. This is a simulation of a 300 gigahertz ISAR image at 100 kilometers away. Relative velocity in LEO of the two spacecraft is 15 kilometers per second. And we can achieve a range resolution of about 2 centimeters. So that's pretty good for being able to look at the surface of a spacecraft and do some conditional monitoring of it, particularly if you have more than one pass. So in order to develop this further, what we wanted to do was to develop an end-to-end simulation capability from the idea, basically, if we want to have, say, a scenario where we can observe a geo asset, all the way through to being able to segment and classify the images that are produced. So we start with our orbit propagation tools. We have custom orbit propagators in Python and MATLAB that we use to narrow down the scenarios to ones that we think would be most viable. By most viable, I mean the ones that fulfill our SWAP criteria, size, weight, and power, and also minimize the amount of station keeping that potentially we have to do. Then we feed our preferred scenarios into SDK. That's what the movies that you're currently watching on a screen show the encounter from the Earth-centered perspective over on the left, and from the monitoring satellite perspective over on the right. Okay, we want to take a close look at the encounter. And we want to build up a picture from a series of encounters. So we then look at a set of encounters from a given trajectory to work out the best one to give us a diversity of perspectives on our target. So on the right-hand side, that just shows the illustration of one encounter and what the geometry of the encounter looks like as the monitoring satellite passes the observed satellite in a little bit more detail than you can see in the lovely movies from SDK. And the coordinate system for the encounters, which are the black dotted lines, each of the encounters is a black dotted line, is centered on the OS. So what this nice shell shows is that you're getting quite a complete picture of what the state of your observed satellite is. Now we want to be able to simulate the images in a reliable fashion. And to do this, we have built a simulator, which is the Graphical Electromagnetic ISAR Simulator for Terahertz Frequencies, which is too much to say at once, so we call it GEIST. And we also need to validate this system. So I'll explain it. It will become clear when I get to the next slide why we've built this and not just used a full wave simulator. So we feed our CAD model into the ray tracer, and then we get, effectively, end up with a scatter map down at the bottom. And then once we've fed the scatter map, the ISAR parameters, we get an ISAR image. So in order to do the validation, we started out with using an antenna because we work on radar. And so we've got a CAD model of our antenna and the real model of our antenna. And we took laboratory images of the real antenna and then used the CAD model to produce the other two images on the slide within a full wave simulator and in our simulator GEIST. And so the laboratory images take about 3 hours in total to set up and produce. The full wave simulation takes about an hour, and this is for a 10 centimeter by 10 centimeter item. It's really small. And GEIST takes 10 seconds. So if we want to build up a library of simulated images, we don't want to be using full wave simulation all the time. We'd much rather use our much quicker method of producing these so that we can take the next steps in our simulation process. So I just wanted to show GEIST working on a geosatellite. So this is a much bigger thing. This is 40 meters end to end from one end of solar panels to the other. And the image on the left shows geosatellite at 75 gigahertz, and the one on the right shows it at 300 gigahertz. And this is at 5 gigahertz bandwidth. So this gives us about 3 centimeter resolution in the images. And I think it's nice. Here's a movie of an encounter. So this is the complete movie of an encounter from the nearest approach where we can see it, which is 100 kilometers away, through closest approach, and then leaving the encounter. And so what you can see is that you can quite easily distinguish not just the body and the solar panels of the spacecraft, but a fair amount of detail on the deployables. Okay, so once we've done all that, and that's a fair amount of work, it actually is one small step in a much bigger picture, which is the ability to do segmentation and classification of the images, which we'd love to do autonomously, and to be able, potentially, eventually, to do this on board, rather than having to transmit all the images to the ground. So we start with our CAD model, we run everything through GEIST, and then we start our classification. So we start with segmenting the image, and then identifying the different sections of the spacecraft. This is a very simple demonstration, sorry. It's just the solar panels and the bus. We can extract deployables using our technique now, but this is what has been published, so that is why I put it up here. So once we have this lovely complete picture of everything that we've done, why would we need quantum to help us? So what we eventually want to achieve is not just the ability to do this with one satellite and one monitoring spacecraft, but to do it from many perspectives with lots of satellites and coordinated operations between them. We'd love to have some complementary on-orbit sensing capability, so things that are not radar, in addition to the radar imaging, and we'd love to be able to do opportunistic as well as planned encounters. So if you have a number of spacecraft working together in a constellation, or even not as a constellation, just similar spacecraft with similar capabilities on board, trying to image the same objects simultaneously, we need high stability, high precision clocking. And that is one of the key field trials of QuSIT, and hence the overlap of this work with the Quantum Hub. Okay, I hope that was illuminating. Thank you very much for listening to me. This is another image, sorry, I forgot to say this at the beginning. This was me attempting to get ChatGPT-4 to produce an image of a whole bunch of satellites with clock synchronization and coherent data acquisition. And I really hope that this is not the dystopian future that we face. So thank you very much.
Thank you, Leah. I think that just goes to prove that AI has got some way to go before it takes our jobs, thankfully.
And the more times I did it, the worse this got.
Excellent. So we've got time for a couple of questions, if there's any. Yep, there's one at the back there.
Hi, I'm Arsha from NSTF RALSpace. I'd like to ask the satellite which is capturing the ISRA images, in which orbit is it operating? Like this is the satellite which is capturing the images of the satellite which are in the geosynchronous orbit. So is the satellite in the same geosynchronous orbit or some other orbit?
It is in a different orbit. We've looked at a couple of, well, more than two, but we've looked at a couple of different scenarios, orbital deployment scenarios in detail. One of them is sort of a Molniya type one, and the other is an inclined geo-orbit that's offset from the target, which will be much more challenging to reach, but produces really lovely imagery. So it will be a compromise between those two things. If the system is targeted at a single high-value asset, if it's more opportunistic, then we don't have to worry about that too much.
Oh, yeah, one here.
Hello. I'm always basic questions, I'm afraid, but the point of this is to check the health of the satellite. What's the end gain from this?
So the end game, I guess the end game is to have a timeline of the satellite's condition, because you can make these passes. I didn't put this on the slide, sorry. Because you can make these passes once or twice a day, you should be able to build up a pretty complete picture of what the condition of the surface of the spacecraft, including the bits that you can't see from the Earth. And it should let you, in theory, with the segmentation and classification algorithms, detect if there's been any damage, or if there, and especially because we can achieve sub-centimeter resolution if someone will give us enough power. Then you should be able to see if there's damage or if there's, for example, a spawned object that has been attached to the spacecraft. I don't think we have many ways to detect that now apart from electronic housekeeping, and even then you might misinterpret what was wrong. So having visual imagery of a surface of a spacecraft would be incredibly powerful.